right, you guys. So today what we're going to do is we're going to be talking about the first section of chapter 12. We did some of this in class already. So I believe we would have gotten through this first example. So I'm going to pick up on this example 2 with the Mentos. Okay, so in example 1, we put all the data in a calculator and we got the information out of a list when we were given the data set. For example 2, we're talking about when Mentos are freshly dropped into a newly opened bottle of Diet Coke, carbon dioxide is released from the Diet Coke very rapidly, causing Diet Coke to shoot out everywhere, right? How much more Diet Coke is going to be shot out of the bottle when there is a larger number of Mentos dropped in the bottle? Okay, how much more? So 2 stats students, Brittany and Allie, decide to find out. Using 16-ounce bottles of Diet Coke, they dropped in either 2, 3, 4, or 5 Mentos into a randomly selected bottle, waited for the fizzing to die down, and then measured the number of cups in the remaining bottle. Then they subtracted this measurement from the original amount to calculate the amount of Diet Coke that was, fizzed out of the bottle. So here's the data set. Okay, so it's the number of Mentos, and it's really just, it would be like one long table down, but I've made it as 2. So it's like, here's one set, like these are ordered pairs, and then these are the rest of the ordered pairs. Okay, now what we've got here is a computer printout, which we actually did when we learned this stuff back in chapter 3 or 4, whatever chapter it was. So like we reviewed in class when we first started talking about linear regression in class when we did the first example from this lesson, when we have this computer printout, here's the A, here's the B, okay? Here is your standard error of beta that we need for the confidence interval. This part here for T under the variable, not the constant, okay? Here under the variable would be your test statistic. And then this here would be your p-value, okay? This p-value amount is always for a two-sided test. So if you actually don't have a two-sided test, then we'll address that as we get there, okay? For this problem as well, you're given the scatter plot of the data set, okay? It gave you the residual plot, and then here is your histogram, okay, of your residuals. So, or you could also have a dot plot of your residuals. So as you remember, you need to hit all of these points for liner. Okay, so these are your assumptions, which are really, really long. Okay, so we have the LINER to help us remember our assumptions when we're working on these. So if we want to start with construct and interpret a 99% confidence interval for the slope of the true regression line, then that's how we know we want to do panic. So our parameter is we're going to let beta equal the true slope of the true regression line, relating the amount expelled in cups to the number of Mentos, okay? So our amount expelled was our Y, our number of Mentos was our X. You need to list which 2 variables you're comparing as we work through that piece. Okay, then as we cruise through, we're gonna do our assumptions. So for liner, the first is linear. We need to double check that our scatter plot shows a linear pattern and that the residual plot isn't curved. That means that it was linear. Okay, we need to check that they're independent, that the amount expelled from one bottle shouldn't affect the next bottle, which is true, right? They're separate bottles. We need to check normal. The histogram back on the previous page that was already given to you doesn't show any outliers or skewness. A lot of times, like on the AP test, when this stuff pops up, if they're going to have you check all the assumptions, they're going to provide graphs to you so that you don't need to spend your time drawing all those graphs because it would eat up all your time. They'll provide you the graphs or maybe even provide you the computer printout and then just expect you to be able to analyze it. All right. E is your equal variances. We just need to check to make sure that the variability in our residuals is roughly the same, which means that they're equal spread. So if we go back here, our residual is pretty evenly spread out. The spread this way and spread this way are pretty much the same. Just like as you're looking here when we did normal, okay? This is okay, we don't have strong skewness, so that was fine to use for there. All right, and then random, the number of Mentos was randomly chosen. That was listed in the problem. Okay, so the name of our test is a confidence interval for beta, our slope. Okay. We're going to have degrees of freedom. Remember, it's n minus 2 for this problem, which would be 14. When you look up 14 degrees of freedom and a 99% confidence on the chart, on the paper chart, you're going to get 2.977. If you are using the calculator and you're doing TCDF, remember that it would be 0.005, because if you've got 99 in the middle, that means you have 1% left for both tails. So it's going to be 0.005 for each tail. So the area, if you're doing, not TCDF, inverse T. Inverse T would be 0.005. We're getting the B and the standard error of the B from the table here. Okay, here's the B. Here's the standard error of the B, this guy. Okay, so the standard error of your B is always going to be with your B. They're going to be together. Okay, and then we can work through that. So we are, as we look at our conclusion, we are 99% confident that the interval from here to here captures the slope of the true regression line. Now, like we talked about in class the other day, all right, it's important to remember that since all variables are positive, okay, if they're all positive or they're all negative, then that means that there's a relationship, right? If all of the values in the interval are positive, that means it's going to have a positive relationship. If all these values are negative, that means it's going to have a negative relationship. If you have some positive, some negative, that's when we don't know if there's a relationship or not. Okay, so if there's some positive and there's some negative, we don't know. Is it going to be a positive correlation or a negative? That's when it's the unknown. But if you do have where they're all positive, then we could make some kind of conclusion, right? That yes, as the number of Mentos increases, then the number of, or the volume of Diet Coke sent out of the bottle would be an increase as well. Okay, so let's take a look at what would happen if we had phantoms. Okay, so when we're working on phantoms, that's when we want to perform a significance test for the slope. All right, so if we've got example 3, infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. Child development researchers explored the relationship between the crying of infants 4 to 10 days old and their later IQ test scores. A snap of a rubber band on the sole of the foot caused infants to cry. The researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. They later measured the child's IQ at 3 years old using the Stanford-Binet IQ test. The table below shows the data from a random sample of 38 infants. Okay, so here are it's like these are ordered pairs, these are ordered pairs, these are ordered pairs, these are ordered pairs. Okay, with the number of peaks right here, right? Measured its intensity by the number of peaks in the most active 20 seconds. So as we're looking through, I'll come back to this in a minute. Here is a scatter plot of the data with the least squares line added. So we want to describe what this graph tells us, right? So as we're looking, and I've made a bunch of notes on here. So here's the scatter plot, okay, which tells us that it's moderate, okay, it's positive, and it's linear. I picked apart some of these pieces. We have the A for the equation. We have the B for the equation, okay? We've got the standard error. We don't need this, don't need this, don't need this ever, okay? That would be if we were looking at it for the y-intercept. Remember, the constant is your y-intercept, and the cry count is what's being attached to your slope, okay? We never use the r-squared adjusted. We know that from previous when we learned this way earlier in the year in the fall, okay? If r squared here is 20.7%, that means r squared is 0.207. So we would need to square root it to get r, our correlation coefficient. And remember, your r has to have the same sign as your slope. If your slope is positive, your r is positive. Your line is positive, right? If your slope was negative, then you would need to remember to make your r negative to match your slope, the relationship. So if we're looking at just B, this is old, okay? What is the equation of your least squares regression line for predicting IQ at age 3 from the number of crying peaks? That's when we did y prime equals a plus bx. A is the constant, b is the slope. So we had y prime equals 91.268 plus blah, 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 x, where x is your number of crying peaks and y hat is your predicted IQ, right? It could be called y hat. Some places call y prime with like an apostrophe. If you wanted to put it with words, you could say your predicted IQ is equal to, there's your numbers, times your number of cry peaks. So this is actually a problem from the previous chapter back in the fall, the type of problem. Okay, now what we want to look at is, can we interpret the slope and the y-intercept of the line we just did? Again, this is also a repeat kind of problem. So our slope would be that for each additional crying peak, our IQ would increase about 1.5 points. All right, because that's how we would interpret. As your x goes up, so does your predicted y. You really should say predicted IQ. I forgot the word predicted. To interpret your y-intercept, right? Your y-intercept is what happens when x is 0, which here would be an infant who doesn't cry, who has 0 cry peaks, will have an IQ of about 91. And again, it would be predicted IQ. All right, because remember, it always needs to be explained in the context of the problem. Now, here is where it's new, part D. Do these data provide convincing evidence that there's a positive linear relationship between cry counts and IQ, and we want to carry out the appropriate test? So, here you are provided your residual plot, and you're provided your normal probability plot. Remember, your normal probability plot is when you have residuals on the x-axis and you have z-scores on the y-axis. That was a normal probability plot. You almost never have to create this on your own. You just need to be able to interpret it. And so as we go through, we're still going to talk about the same ideas, right? P is your parameter. We're going to let beta be the true slope of the population regression line relating cry count to IQ. We're going to say our null hypothesis is that b equals 0, because if your slope is 0, that means there's no linear relationship. And if b is greater than 0, then that means that it's a positive relationship, okay? Okay, positive slope. So now as we go through Liner, okay, I've got it all here. So linear, it's a moderate, or you could call it a weak positive relationship, linear scatter, and the residual plot is random. So when you look at your scatter plot, it's positive, it's kind of weak, kind of moderate. You could look at it either way, right, and that's okay. Your residual plot has randomness. Remember, residual plots, you don't want a U, okay, and you don't want a U the other way. Independent IQs are not related to each other. We need to check our 10% condition. Our population of all newborns should be at least 380. Okay. Normal, we're allowed to use the normal probability plot. Hopefully your normal probability plot is going to be nice and linear, right? And then that's good. But in a linear or straight normal probability plot means that the original data set is normal. This one's showing a slight curve, but we're going to proceed anyway. So I would say that. Okay, you also could go back if you wanted. You could put all that data in your calculator and like draw a dot plot or something. It's a lot of work. Considering they already gave you a normal probability plot, I would just use that. You're going to have equal variance. Your residual plot shows fairly equal amount of scatter, right, around your horizontal line. So the vertical scatter and the horizontal scatter from that line, they're pretty even, minus this point. They're all pretty evenly spread out above and below. All right, so then that means that they're going to vary equally from each other, equal variance. And we were told it was a random sample. The name of our test is a t-test for slope beta. That's always what it's going to be. All right. Our formula, I just put this is actually what I told you I would come back to. All right. So here's the formula for your test statistic. Okay, and we're still going to use degrees of freedom or n-2. So we're going to plug this in. On the output on the front, here's the B minus the beta, right? So here's the beta here, is 0. It's always going to be 0 for us, for right now, okay? For like this year, our level of doing these computations, we're always going to use 0. Okay, and then you're divided by the standard error of beta. So this and this are the same two things we used for the confidence interval. Okay, and we get 3.07, right, which is also on here. 3.07. So you could just grab it from here. Remember, your p-value is also here as well. So you could use a TCDF to get that p-value. But remember, the p-value that they give you is always already doubled. It's the two-tailed test. So that is something you have to be careful of. You are used to, when you do like TCDF in the calculator, getting it and then doubling it for a p-value, right, for a two-tailed test. If you're given the computer output, it's giving you the two-tailed test already doubled. So if you have a one-tailed test like we have here, you have to cut that in half, which is why it's 0.002. Now you'd have the same conclusion, but it's going to be still considered wrong because you're using the wrong p-value. So as you're looking at this, our p-value is less than alpha, which means we reject the null, which means yes, we would have a positive linear relationship between, you would write a more thorough response than I did for my notes, I'm sorry, between cry count and IQ of the newborns, okay, or the cry count of the newborns and their IQ when they are 3 years old. All right, so take a look at this next problem. Oops, I just dropped my index card. All right, take a look at this one and then we'll see, okay? Customers do we want to know, do customers who stay longer at buffets give larger tips? So Charlotte, who worked at an Asian buffet, decided to investigate this question for her second semester project. While she was doing her job as a hostess, she obtained a random sample of receipts that included the length of time in minutes the party was at the restaurant and the amount of tip that they left in dollars. So it'd be great if you guys could just pause this, use pencil, and just try this whole problem right now on your own. See if you can put your application together. The first couple parts are what we learned a while ago. And the second couple parts are what we are going through now. Okay, I'll go through it too, but I strongly encourage you to try this on your own, at least to see if you can digest the pieces of information that you had. All right, we've got our constant is our A, our y-intercept, the time, right, the one with the vocab word is our slope. So then here's the standard error of our slope. Here's the p-value. This is the test statistic. Okay, you're not using anything from the y-intercept, the constant, okay? You're not using r squared adjusted, you're just using r squared if you need it. They're giving us the data set. They gave us the residual plot. They gave us the scatter plot and the normal probability plot. Remember, normal probability plot is residual and your z-score, okay? So hopefully you can figure out what the equation is and define your variables. Okay, we want to make it where it's, here's your equation, pulling the A and the B from above, where y prime or y hat is your predicted tip and x is your length of stay in minutes. Okay, the unit of time is important, okay? We're going to talk about breaking these down, all right? If you want to interpret your slope of your least squares regression line, hopefully you had that for each additional minute that a party stays at the buffet, the predicted tip is going to increase about 3 cents. I made a note up here that we need to remember that R is your correlation coefficient. R squared is your coefficient of determination. All right. So that one, R squared, our coefficient of determination, was one where we had like a canned sentence. We had a plugged in sentence that we always just kept reusing. Okay, we just swap out the variables. And it was blank percent of the variation in Y, our variable for Y was tip amount, is accounted for by the least squares regression line for, and then you plug in your X variable. All right, so we would have 13.2% of the variation in the tip amount is accounted for by the least squares regression line for the length of stay in minutes. Now it's going to ask you to do your hypothesis test. If we have a positive linear relationship, okay, it's just a coincidence that these both had a positive linear relationship. We could also do a negative linear relationship, which I'm sure we'll get to in our examples. All right, you've got your parameter, and then your hypotheses, and then we have our assumptions. Okay. So as you read through, We selected with non-replacement, which means we need to check is our population at least 10 times our sample size. Our normal probability plot that was provided to us on the previous page looks roughly linear. Our residual plot is showing an equal amount of scatter. Our receipts were randomly selected. And then as you go through here, we have a t-test for slope beta. Your test statistic, you can just get the value from the front, or you should know how to plug it into the formula. Remember, it's lowercase b minus beta over the standard error of b. Your p-value, you're going to take the p-value on the front and you're going to cut it in half using 10 degrees of freedom because it's n minus 2. All right, so your p-value is greater than alpha, which means do not reject the null, which means we can't conclude there's a positive linear relationship, which means we can't conclude that those who stay longer actually leave bigger tips. That's not a conclusion we can make because we didn't reject the null. Right? If you don't reject the null, then that means we can't say it's a positive linear relationship. I know this is a lot of content. I hope you took marvelous notes today. Of course, we're going to practice. Yes, I know. Don't be mad at me. I didn't come up with these assumptions, but they are important for you to be able to go through. And good job taking great notes today.